For Lesson 4, Chapter 4, we're going to be looking at chemical reactions and solutions.
Now that we've learned about chemical equations and some of their features and how to balance a chemical equation, let's look at some common types of chemical reactions. The first one we're going to explore is combination reactions, also referred to as synthesis. So what exactly is a combination reaction? And how do you tell just by looking at the chemical equation itself? Well, combination reactions will have two or more reactants. So in the case of this reaction scheme, there's just two reactants represented by the letters A and B. Those two reactants combined, hence the term combination reaction, to form one product. So looking off to the right here, the atoms are represented, so we have one A atom and one B atom combining, so they're forming a bond to form one final compound. Some examples of combination reactions are below. So the formation of water would be one, because we have two hydrogen gas compounds and one oxygen gas compound forming two water compounds. Ammonia, same thing. We have nitrogen gas and hydrogen gas combining to form ammonia. Next is decomposition reactions. So these are the opposite direction of those combination reactions. So in decomposition reactions, you're going to see just one reactant, which will be a compound. And what happens to that one reactant is it actually breaks apart, so bonds are being broken, to form two or more products. So opposite. Some examples. We have three different ones shown here. You'll notice they have names: thermal decomposition, electrical, and photolysis. You don't need to know the beginning terms, the difference between thermal, electrical, and photolysis. You just need to know or be able to recognize when given these chemical equations that they are indeed decomposition reactions. And you can tell that by seeing that there's only one reactant. I know there are two compounds, or two molecules, I should say, of this particular compound, but it doesn't matter. There could be 5 molecules. The important thing is that only one type of compound is present on the reactant side. So we have one type of compound breaking apart into two different products. In this case, potassium chloride and oxygen gas. The second example, we have one type of compound present here, so aluminum oxide, decomposing or breaking apart into aluminum and oxygen. Now the last one looks like we have peroxide here. So two molecules of peroxide are decomposing or breaking apart to form water and oxygen. So one type of reactant breaking apart into two or more products. That's the definition of a decomposition reaction. Single displacement reactions are next. They are sometimes referred to as single replacement instead of displacement, so just know those terms are interchangeable, replacement and displacement. So the general reaction scheme for these, as you'll see below, we have one compound. So here we know it's a compound because we have atom A with a bond to atom B. So we have one compound reacting with an element by itself, in this case, element C. So what happens in a single displacement reaction is that atom C is going to displace one of the atoms in the compound. So it looks like, in this case, atom C is displaced or replacing atom B to form a new product where A is now attached to C instead of B in the product side. Since C replaced B, now B is an element by itself on the product. So below are some examples of this. The first one being a redox reaction, and we'll talk more about redox reactions in later chapters, but most redox reactions are single displacement reactions. So you can see in this example, we have copper 2 sulfate. If you remember from naming, since copper is a transition metal, you need the Roman numerals after representing its oxidation number. So copper 2 sulfate reacting with zinc. So copper 2 sulfate, that's the compound, right? Copper with a sulfate ion. Now zinc is the element by itself. So what's going to happen here is zinc is going to take the place of copper. Now how do I know that zinc is taking the place of copper and not the sulfate? Well, because a metal always replaces a metal. Or to be more specific, a cation, which zinc would be a cation once it's in a compound, replaces another cation. So once zinc kicks copper out, that leaves copper by itself on the product side, and now zinc is in a compound with the sulfate, zinc 2 sulfate. Now let's look at this halogen example below. We have chlorine gas, which is an element by itself. I know it has this 2 beside it, but remember, chlorine is one of those diatomic elements in nature, meaning that chlorine never exists by itself. So there's never one atom of chlorine just floating around in the air. It's too unstable. So what it does is it pairs up with another chlorine atom to stabilize itself. So Cl2 is referred to as a diatomic element. So it is an element by itself, even though there's 2 present. So we have a chlorine element by itself reacting with a compound. In this case, we have potassium iodide. It's a good time to practice your naming. So now what's going to happen is, since chlorine is a halogen and likes to form an anion, a negatively charged ion when in a compound, it's going to replace the anion or the negatively charged compound. So it's going to replace iodine in this case. So when chlorine replaces iodine, it kicks it out, leaving iodine now by itself. And notice iodine is a polyatomic, or not a polyatomic, excuse me, a diatomic. That's why it has the subscript of 2, because iodine is unstable. One iodine atom is unstable by itself, so it finds another iodine atom to pair up with. And then now chlorine is paired up with potassium to make potassium chloride. Next, we're going to look at how to tell if a single displacement reaction will occur or not. Because even though a reaction scheme is written down, it's not guaranteed that the reaction is going to go to completion. So how do we tell? Well, since a lot of the single displacement reactions we're going to be looking at are redox reactions, that's the example we're going to use to figure out if this reaction will take place or not. So the general rule is that a more active metal replaces a less active one. So in this reaction scheme, zinc is the metal, in this case, by itself. So as long as zinc is more active than the metal it's trying to replace, which in this case is copper, then the reaction will move forward. So how do we tell if zinc is more active than copper? The activity series of metals will help us figure that out. So you might recognize this table. It is one of the tables that you needed to put into your lab manual as one of the reference sheets. So what we do is we look for copper and zinc on this table. Finding copper looks like it's pretty low on the activity series, which is good in this case since that's the metal that is being replaced. Lower the better. Zinc is the metal that's trying to replace copper, and notice it is much higher on the activity series. Since it is higher on the activity series, that means yes, it will replace copper, because it means it's more active than copper and it can replace copper. So that's how we're going to be using that table. We will look at that table a lot more during lab and when we talk more in depth about redox reactions. The next type of reaction we're going to explore is double displacement reactions. For double displacement reactions, you'll notice that the reactants and the products are both compounds. So we have 2 compounds as the reactants, 2 compounds as the products. So what happens in a double displacement reaction is they actually switch partners. So I like to see double displacement reactions, or describe double displacement reactions, kind of like a dance. So if you think of ballroom dancing or any kind of dancing that needs partners, what happens when you are doing a dance class or dance partners is sometimes you switch partners, and that's exactly what they're doing in a double displacement reaction. The nice thing about double displacement reactions is they usually follow the same pattern as well. So you can see we have element A and element B together in a compound on the reactant side. We also have element C and element D together in a compound. Now what happens is the outer elements, in this case A and D, are going to combine to form one of the products, compound AD on the product side, and then the inner elements, in this case B and C, are going to combine to form the other product. Now this is almost always the case. The outer elements combine to form one product, the inner elements combine to form the other product. This is important because at some point, particularly in lab, you're going to have to predict the products of double displacement reactions. So it will be very helpful for you to know that the outer elements combine to form one of the products and the inner elements combine to form the other. So let's look at some specific reaction examples. For double displacement reactions, they can be broken down into 3 subcategories. One of them is a precipitation reaction. So precipitation reactions, how do you know if the double displacement reaction qualifies as a precipitation? Well, the word precipitation stands for precipitate, and a precipitate is the word for solid in chemistry. So that means that a solid is forming. So you should see a solid in one of the products. How do you know if a solid formed as one of the products? Well, you look at these little letters in parentheses that come after each element or compound. So remember the letter S stands for solid, so that means this particular example is a precipitation reaction because solid is one of the products. You'll also notice that the other letters are AQs. Those stand for aqueous. That's when we have a solid that is dissolved in water. The next specific reaction example for double displacement reactions is an acid-base neutralization reaction. So for an acid-base neutralization reaction, the properties are going to be, you're going to have an acid as one of your reactants. So in this case, we have HA representing the acid. And for this course, how do you know if it's an acid? Well, all the acids we're exploring for Chem 1 are going to start with hydrogen. We already named some acids, monatomic and polyatomic acids, and they all started with a hydrogen. The base is going to have an OH in it for this course because those are the only bases we're going to be looking at in this course. Keep in mind there are other types of bases. It's just not ones we're exploring in Chem 1. So reactants, acid, and a base. The products then are going to be a salt, and that's what XA is representing, and water, H2O. Notice water has an L by it because it's a pure water with nothing dissolved in it. The last type of specific reaction example is a gas-forming reaction. So just like with all double displacement reactions, we have 2 compounds on the reactant side switching partners. Notice we have the outer guys, B and A, teaming up to form one product, AB. And then the inner elements, C and D, pair up to form the other product, DC. But notice, how do we know it's gas forming? Because one of the products has a G by it, indicating it's a gas. Combustion reactions are reactions in which you have a fuel source, and the fuel sources that we will see will mainly be made up of just carbon and hydrogen. Some of them will also have oxygen in them, but carbon and hydrogen will definitely be present. So a fuel source reacting with pure oxygen. Remember, oxygen is one of those diatomics that likes to pair up with another oxygen atom to stabilize itself. The products are always going to be carbon dioxide and water every time. So if you see the products as carbon dioxide and water, and the reactants have oxygen and a fuel source in them, you can guarantee that it is a combustion reaction. Some specific examples are below. Burning car fuel is the first one where we have carbon and hydrogen, C8H18, being the fuel source. reacting with pure oxygen. A combustion reaction occurs to form the products carbon dioxide and water. Now notice the coefficients in front of these. Very, very large coefficients. So balancing combustion reactions can be very difficult because of the very large numbers included. So whenever you are balancing a combustion reaction, remember to balance the oxygens last. So why do you want to balance the oxygens last? Because in the products, oxygen is in two separate places. We have oxygen on the carbon dioxide and we have oxygen in water. So save it for last. Hopefully it'll balance itself out and save you a lot of time and energy. Now the next example is burning sugar. So this example has the fuel source containing carbon, hydrogen, but also oxygen. And that's fine, that's still a fuel source. But notice the other reactant is still oxygen, just like it should be in all the other examples. Products, carbon dioxide, water. Let's look at an example. So what type of general reaction type are the following equations? So for general reaction type, we have 5 that we had covered so far. They are combination reactions, decomposition reactions, single displacement, double displacement, and combustion. So let's look at example number 1. In example number 1, we have zinc 2 carbonate, which is a compound, reacting with another compound, and it looks like what's happening is they're forming 2 new compounds. So this should be pretty straightforward to see that it is a double displacement reaction. And remember, for double displacement reactions, just for practice, it's always the outer 2 elements combining. So in this case, zinc and hydrogen, or sorry, not hydrogen, iodine, to form zinc 2 iodide as one of the products. And then the inner 2 also combined. So we have the carbonate ion combining with hydrogen to form the other product. The next example, we have a compound made of carbon and hydrogen reacting with an element, oxygen. And the products are carbon dioxide and water. So what would that be? It's a combustion reaction because the C2H6 is the fuel source and it's combining with oxygen to cause a combustion reaction that will produce carbon dioxide and water. The last problem, we have just one reactant, and it looks like that one reactant is breaking up into 2 separate products. So whenever you have one reactant and 2 or more products, it is going to be decomposition. Next, we're going to look at what type of specific reaction are the following equations. So the word specific, these are not just the 5 main ones. These are also the subcategories. And we saw most of the subcategories with those double displacement reactions. So if you remember, the double displacement reactions had subcategories of precipitation, where a solid was formed, gas forming, where a gas was formed, but also acid-base neutralization, where acid and base were combined to form a salt and water. So let's look. The first one, we have HCl reacting with NaOH. So 2 compounds reacting to form 2 new compounds. So this looks like a double displacement reaction at first glance. Since it is double displacement and they're asking for specific reaction type, we need to dive a bit further. So looking more closely, is it a precipitation reaction? Well, for a precipitation reaction, we should see a solid forming for one of the products, and it looks like we have an aqueous and a liquid, so it's not precipitation. Gas forming was another type of double displacement reaction, but I don't see any gases that were formed as products either. So it must be neutralization. And looking at the reactants, that holds true because HCl is hydrochloric acid, NaOH is sodium hydroxide base, so we do have an acid and a base reacting together, and the products are formation of a salt, in this case sodium chloride salt, and water. So this would be a neutralization reaction for number 1. Now looking at number 2. For number 2, we have aluminum, an element by itself, reacting with oxygen, another element by itself. And it looks like they're forming just one product. So we have two reactants combining to form one product. So what type of reaction would that be? Number 2 then would be combination or synthesis reaction. So I'm going to highlight that in blue for number 2. Now let's look at number 3. Number 3, we have iron 3 chloride, if we're naming it correctly, with potassium hydroxide. So it looks like we have two compounds forming two new compounds for the products. So with that, we know it's a double displacement, but they asked for specific. So what type of specific reaction is it? Well, since it's double displacement, we know that the outer two elements, or polyatomics in this case, are going to combine. So we have iron combining with the polyatomic hydroxide to form iron 3 hydroxide on the product side. And then we have the inner two, potassium and chlorine, combining to form potassium chloride. Now, it's not a neutralization reaction because we don't have an acid as one of the reactants and we don't have water as one of the products. Is it a precipitation reaction? Well, I do see an S for solid after the iron 3 hydroxide, so since a solid formed, I would call this precipitation. So precipitation reaction for number 3. Now let's look at some definitions. So we're going to look at solutions and solvation. So what exactly is a solution? We've already looked at what a solution is. Whenever we see an AQ in any of those chemical reactions that we've been looking at, that is a solution because what the AQ stands for is aqueous. And aqueous means that there was a solid dissolved in water, making a solution. So a solution is made up of two or more parts, a solvent and a solute. So a solvent is going to be the substance in greater amount. So in the example I just described, that would be the water that dissolved the solid, because the water would be present in a larger amount. Now the solute in the example I just said, the substance in lesser amount would be the solid that I dissolved. Now with solutions, we have several different types of solutions depending upon what type of solute was added. So the types of solutes that we're going to explore are first going to be an electrolyte. So electrolytes are solutes that dissolve in the water and form ions in the water. And that's the example that we have shown in the picture. So this big cube guy here with all the pluses and minuses stacked very nicely, that is going to be the solid, the ionic solid. When that ionic solid is added to water, what happens to it is it separates out into its ions. And that's what we are seeing here with these negatives and these positives. So they separate into their ions and are surrounded by water molecules. They make electrolytes since there are now charged particles in the solution, and those charged particles can then conduct electricity. So lots of properties with electrolytes in solution. So it's always ionic compounds that separate into their ions and can conduct electricity. Next, we're going to look at non-electrolytes. Non-electrolytes then are going to be covalent compounds. So remember, covalent compounds shared electrons. So since they're sharing electrons, there's no charged particles. So they're not going to separate into their ions once they're dissolved in solution. And since they don't form charged particles, they also cannot conduct electricity. And if you remember right, covalent compounds are compounds that are made up of just nonmetals. So that's how you can tell if it's going to form a non-electrolyte. If a covalent compound is dissolved, meaning a compound with nonmetals. The other types of solutes that we'll see will be acids and bases, but we're going to focus on the top two. So looking more closely at electrolytes versus non-electrolytes. What would make a strong electrolyte? So what would make a strong electrolyte would be a compound that completely ionizes in solution and strongly conducts electricity. So that is going to be the middle picture here of KCl, potassium chloride. So potassium chloride is an ionic compound made up of potassium metal and chlorine, which is a nonmetal. So since it's made up of charged particles, when it dissolves in water, it's going to dissociate completely into its ions. That's why we see little plus ions and little minus ions in solution. Due to those charged particles, it can therefore conduct electricity, and that's why we see the brightest light bulb. For a weak electrolyte, an example of a weak electrolyte would be this acidic acid solution. So weak electrolytes are going to partially ionize. That's why you see some neutral compounds that are still together that have not ionized or separated into their elements or atoms. But you also see a few charged particles. So partially ionized, not completely. So it still can conduct electricity since there are charged particles in solution. There's just not as many as there are in a strong electrolyte. So we see a weaker light bulb or poorly conducted electricity. The last one will be the non-electrolytes. So non-electrolytes do not ionize at all. So no charged particles in solution, meaning they cannot conduct electricity. The example here is ethanol, which is a covalent compound made up of carbon, hydrogen, and oxygen. So all nonmetals that do not dissociate when dissolved in water, meaning no electricity, so light bulb does not light up. Let's apply what we just learned to an example. Which of the following, when dissolved in water, would create a bright light or conduct electricity? So kind of ignore the bright light part. Doesn't matter how bright the light is. They're just seeing, will any of these conduct electricity? So how do we tell? Well, if it's ionic, having charged particles, then yes, it will conduct electricity. If it's covalent, made up of all nonmetals and does not dissociate into charged components, it will not conduct electricity. So let's look at number one. Number one, magnesium chloride. Magnesium is an alkaline earth metal. Chlorine is a halogen, a nonmetal. So we have a metal with a nonmetal, which means it's ionic. If it's ionic, it will separate into its charged particles, magnesium with a +2 charge and chlorine with a -1 charge. So yes, it will conduct electricity. Next, we have ammonia, or if we're naming it systematically, it would be nitrogen trihydride. Nitrogen and hydrogen are both nonmetals, making this a covalent compound, so it would share electrons and not form charges, meaning it could not conduct electricity, so it would be a big no. Zinc 2 sulfate. So zinc is a metal, it's a transition metal with a +2 charge. SO4 is a polyatomic, hopefully that you've memorized from the polyatomic table. It's sulfate with a -2 charge. So since this compound is made up of charged components, it's ionic, and it will dissociate when dissolved in water into charged components that can conduct electricity. So a big yes. Last but not least, we have sugar. Sugar made up of carbon, hydrogen, oxygen. All of those are not metals, making it a covalent compound. And we would say no, it does not conduct electricity.